Guys, wasn't that last video awesome? We saw those pillow lavas coming out of the very ground, actually porch, and spewing onto each side of the mid-ocean ridge, the starting point of what we call plate tectonics. This plate tectonics theory. You know, when Alfred Wegener, back in the 1930s, when he first suggested this, everybody thought he was nuts. He actually suggested, because South America and Africa appeared to him to fit together like a puzzle, he inferred, based on that at one time they were together. Everyone's like, oh yeah, whole continents are moving, Al, go have another beer. No way, no way. And then the evidence started mounting in that not only on each side of the ridge do they look like they go together. This is amazing. If you take fossil evidence here and you hook it up and look at fossil evidence here, fossils that only exist here in Africa only exist here in South America. And fossils that only exist there. And rocks and minerals of equal type along this coast match up to rocks and minerals of equal type along this coast. Mountain ranges lined up, glacial formations lined up. It's not just a matter of them looking like they go together, although that's a pretty good piece. Everything, especially when you combine them at this mid-ocean zipper. And look it is a zipper. And what's driving it is the convection currents in the mantle, called in your reference table the asthenosphere on page 10. The asthenosphere driving the crust, the oceanic crust, part of the lithosphere. The crust being the top part of that lithosphere. So the asthenosphere is the fluidy part of the mantle, a semi-rigid part. Then you have the rigid mantle, and the very, very top part you have the crust. And as we talked about, you have two different types of crust, oceanic and continental. Since we're in the ocean, when we're along the mid-ocean ridge, this 46,000 mile long zipper, there's Iceland, where it got extra active, splitting the earth apart by driving forces. Now, why don't we notice it? Why do we have a hard time even believing it? Because it's only happening about this much on each side of the ridge. That's this much on each side of the ridge per year. I mean, what are you going to do? Watch it? Not too exciting. Can you see the lava come out? Can you see the pillows coming out at the mid-ocean ridge? Yeah, we can see that. We can film that stuff. In Iceland, we can see it happening. But we actually can't see it being torn apart. Once in a while, we can see it being jolted apart with an earthquake. But that would have to be the right place, the right time. This picture is actually from Iceland, guys, where there's a bridge. This side belongs to the North American plate. It actually belongs to the North American plate. And this side belongs to the Eurasian plate. You are actually seeing the boundary between the North American plate and the Eurasian plate because there is no actual Atlantic plate. The Atlantic plate is the meaning of South American plate, African plate, North American plate, Eurasian plate, splitting apart, or what we call divergence. Well, notice that when we look at the chart in the reference table, which is on page 5 of your reference table, we have the chart on plate tectonics. Now, I want to show you how real, wait right there, how real these pillow lavas really are. I know you can still hear my voice. These are pillow lavas in action, and check this out. Just listen, guys. You don't have to see me. You don't have to see me. Look at that. You want to see this. You want to see this. Look it. Does that not look like what we saw outside? Red hot in the center. Look it. Like a turd. Just like we saw outside. Pillow lavas of basalt. Mafic rock squeezing down, losing its air, and forming the newest rock on the planet. That is happening right now at the mid-ocean ridge. I mean, isn't it? It's just absolutely fantastic. We'll look at this video in just a few seconds. So here we are, right here, and let me get my clicker. It's right here. So I'll be able to forward this for you guys. And the plates are moving apart. This is where it starts. This is called divergence. Now, if they have divergence, sooner or later the plates are going to hit and collide. In fact, if we look at this, right here, this is your chart. This is your chart on page 5 of your reference tables. And what it shows is a key down here. You guys, everything is really on this chart. This is amazing. Here's the mid-ocean ridge, and notice those two lines. it shows that it's what kind of motion, divergent or convergent. No mystery. If it's like a double line, it's called divergence, usually broken by transform faults. What are transform faults? Things like the San Andreas Fault. A transform fault is where the plate doesn't split apart, but shifts apart like that in a lateral motion, a horizontal motion. We'll show that more when we talk about the San Andreas. So what you have are these little offsets and these divides. Offset and divide. Some places it's just a divide. Like there's a really long place of that right here along the East Pacific Ridge. Here along the Indian Ridge, it's just dividing. For the longest time, there's no offset in that divide. But when it's dividing, it's divergent. Divergent. Kind of like we talk about dry areas with wind systems on page 14 of the reference table. When things split apart, that means clear out as far as weather. When they converge, that means bad weather. Divergent, convergent. So, where the plates come together, you have convergency. Now, one of the most famous places in the whole world where that happens is where part of the ocean plate, called the Nazca plate, is diving underneath the South American plate. Now, why did I say diving underneath? Well, I'll explain that in a second. That motion is called a subduction. It says the subducting plate doesn't have the boxes. I think of these boxes as actually teeth. And I think of the subducting plate taking a bite out of the overriding plate. So here is the subducting plate, the heavier plate, the more dense plate, and it's taking a bite or going underneath the South American plate. Well, guess what you have all along the coast of South America? You have volcanic mountains. We call those the Andes. Okay, let's actually look at that form of subduction where you have an oceanic plate hitting a continental plate. And here it is, right here. Actually, we're going to do oceanic hits continental right now. So here it is along the coast of South America. Here's the Nazca plate slamming its way, and this is how it would look. This is a basaltic plate. This is oceanic plate. Page 6 of your reference tables says that it's mafic. It's more dense. Page 10 says in the upper right-hand corner, says its density is 3.0 as compared to 2.7 continental plate. So what's going to happen really is the continental plate is not really even going to stand a chance. So if the oceanic plate is diving into it, here we go. What's going to happen is the oceanic plate is going to go underneath the continental plate. In fact, it's even going to mush it up even more, and it's going to create friction. That area is called a subduction, and it also forms a deep sea area called the deep sea trench. Look at all the heat being generated, and what you have are these volcanic mountains. The same thing is happening on our introductory video when we saw the Space Needle go down in Seattle. Okay, what's happening there, in fact, let me go to the diagram right here. What's happening in North America is you got this little remnant plate, a remnant plate of oceanic material called the Juan de Fuca plate. And the Juan de Fuca has two things going on. It's got a little spreading center there called divergence, and you see the teeth? Whenever you see the teeth, that means plates are slamming together. You have a piece of ocean plate going underneath the continental granitic North American plate. And because of that, you have mountains here called the Cascades. Mount St. Helens blew its top in 1980. It's still, even though it's inactive right now, still considered to be an active volcano. That whole ridge of Cascades is potentially active. Although there's one that actually blew its top over 6,000 years ago called Mount Mazama, which today is what tourist attraction for the world, called Crater Lake. Actually the deepest lake in North America. It goes down over 1,900 feet. By comparison, Lake Superior only goes down 1,300 feet. I say only, even though it's really deep. Like the deepest part of Lake Erie is like just over 200. Mount Mazama is the crater left by an enormous exploded volcano because of that subduction. Oceanic plate hitting continental plate. Let's go back. So there we go. There it is. Now, an oceanic plate doesn't always hit a continental plate. Sometimes you have a continental plate that hits a continental plate. And let's look at this. So we have two continental plates. Nowhere is this more evident in the world than the Himalayan mountain range, where you have India, which was out in the ocean, which for millions of years has been sliding into and met up with now and continues to go into Asia. India slamming into Asia. And as India slams into Asia, it basically is kind of like two sponges smashing together. I have an assistant that has a sponge right behind her that will give it to me right now. And here it is. So what you have is two spongy plates. They're both continental. They're both granitic. They're not as rigid. They're not as dense. And when they combine, oh my gosh, when they slam into each other, they just form a big mush. The biggest mush on the planet is the Himalayan mountain range. And there it is. And it's because both plates are less dense. You have the asthenosphere below it, where the convection cells are driving it. Here, this plate is a little bit more dense. The reason why the Indian plate is a little bit more dense than the Eurasian plate is because it has more pieces of oceanic material, oceanic magma. Because it's got more constituents of oceanic magma, it's slightly more dense. And then you have the most fantastic collision that there is, and that is when oceanic hits oceanic. Because when oceanic plate hits oceanic, I could use these two rocks to demonstrate. There's not going to be a give. In the end, they're both super dense plates. In the end, one might dip below the other. In fact, eventually it will, forming a subduction. But it's not going to go without pain and suffering. It's going to die below it, and the other plate sitting on top of it is actually going to push down on it, making these subductions the deepest, most violent subduction actions on the surface of the earth. A good example is the Philippine Islands. A good example of the deepest trench is the Mariana Islands. You have two. Notice there's no bulging up. It doesn't bulge up like the continental. Let me go back and let me show you how that one was. See, when oceanic hits continental, continental buckles up. When oceanic hits oceanic, that doesn't happen. Instead, this heat builds up and magma pops its way to the surface, not to be gross, but just like an exploding zit on your face. It just pops right through. And as it pops through, it forms these islands that are nothing but volcanoes. All of the Philippines, all the island mass is all the living area of the people is just a series of volcanoes. And it's like that way in the Marianas. This is where ocean plate hits oceanic plate, forming what we call an island arc system. And basically people have taken to living on those. Now, so we have convergent and we have divergent. We also have transform. The best example of transform, although the transform is that lateral motion that occurs along all mid-ocean ridges, in addition to spreading, they're also shifting. The best example is where it happens on the surface of the earth. And in the United States, by the way, this is a photograph. This isn't an artist's conception. This is a photograph where you are actually seeing North America, or actually I should say, depending on how this video was taken, how this photograph was taken, you're seeing North America on one side, and you are actually, let's say that this is the Pacific Ocean plate on this side and the North American plate on this side. And if this is the Pacific Ocean on this side and the North American plate on this side, there's a shift like this. So instead of shifting apart, the shifting is horizontal motion. Now in 1906, one of the worst movements ever occurred along this fault zone called the San Andreas, where it actually shifted like that, okay, more than 20 feet. More than 20 feet. Displaced railroad tracks, started the city on fire of San Francisco because everyone was heating with oil lamps at that time. And something else more interesting, all the pipes and all the water systems in the ground were broken so that when they went to put out the fire with the hoses, no water came out. The city of San Francisco burned to the ground in 1906. A real testament to human ingenuity and ability to overcome crisis, like now, to overcome crisis when we have to. Sometimes necessity is the mother of invention, and we do survive. Anyways, so here we go. There's the motion. That part going that way, this part going this way. I just showed it the opposite, but that's how it's going. This part's going north, this part's going south. And in the video, we actually saw that there was an extension of that up in Seattle, which could happen. So this is a transform boundary. Now to go back to the map, right here. So transform looks like that. Transform the single line. Once again, there are many transforms along all the mid-ocean ridges. Some extended places where it's just divergent, and there's convergent. Guys, sometimes, oh my gosh, questions on this are so easy. Label convergent and divergent areas. Hello, they're right there. Label transform areas. And some areas we're just not too sure about. Like where we have dashed lines, we're not exactly sure what's going on. So how do they label it? Complex or uncertain boundary. Now, we expect, once again, when you go from South America to Africa, the youngest rock, we saw that outside, and the rock gets older. Youngest rock coming out of these ridges today. Youngest rocks on the earth today. Youngest rocks on the earth today. Red hot magma coming out of the ground. We expect it there. We expect St. Helena to be a hot spot. We do not expect the Canary Islands to be a hot spot. We do not expect Yellowstone to really be a hot spot. And we most definitely don't expect Hawaii to be a hot spot. Almost all volcanoes and earthquakes occur together. When they don't occur together, what is it with these random, super deep mantle hotspots? We know that they exist. We can try to explain they exist, but we are still uncertain about their actual existence. But they do show us that plate tectonics is very real, and plate tectonics is happening. For instance, we know that as the plate moves, the Hawaiian Islands are formed. We know that the whole Pacific plate is in motion, and as it's in motion, as the plate gets to the hot spot, volcanic activity occurs. For instance, there's a lot of volcanic activity in the main island of Hawaii. There's also a reason why the main island of Hawaii is the largest. It's the newest. And because it's the newest, it hasn't been beaten down by erosion with wave, wind, and sea. So, let me show you what's going on in Hawaii right now. Stay right there. Just got to show you what's going on, and it's right here. And we'll put on the sound. Oh, after this brief commercial. Darn it, I forgot to just show it. Actually, I have it up here already, guys. So now let's show it. Here it is.
Eruption in Hawaii is threatening to cause even more destruction this morning. The Kilauea volcano on Hawaii's Big Island has spilled huge amounts of lava for more than 3 days and nights. Around 1,700 people living nearby have been evacuated because of the lava and poisonous gas.
The lava has destroyed at least 31 homes and other structures. Hundreds of earthquakes have rocked the area, and more volcanic cracks opened in the ground over the weekend.
That's what you call lava. And poison.
He's outside Leilani Estates in Pahoa, Hawaii. Carter, good morning.
Good morning. This community is locked down. Residents are not going inside right now. In fact, emergency management put out a cell phone warning on Sunday evening telling everyone to get out of the neighborhood. But we understand there are some people inside, and police are not going in to get them out. From the air, lines of smoke show where lava is flowing through Leilani Estates as homes continue to burn.
Up here in the helicopter, you can really get an idea of the scope of the destruction below. You don't see any firefighters down there because there is nothing they can do. This is an unstoppable force.
The lava is consuming
Look at that, guys.
path, including trees and homes.
The newest rock. Oh my goodness.
Eruption.
Newest rock on the planet.
A few more pretty extensive flows. Seems like there's a lot of magma under the ground.
Look at that
There's no
rift.
sign of slowing down.
At least 10 fissures have opened up in Leilani Estates, which is on the eastern slope of the Kilauea volcano. In some cases, the eruptions were so violent.
They said, what slope? They said the eastern slope, because that's where the volcanic activity is. What we're going to do is we're going to end this video now, and we're going to show you a demonstration of how the Pacific plate is moving and how Hawaii is formed in our next video segment.